Today we're going to do an example of solving an inhomogeneous linear ordinary differential equation with constant coefficients using the annihilator method. So our differential equation is here, y double prime minus 3y prime minus 4y equals 15e to the 4x. And our plan over here on the right is first we want to find the complementary solution y sub c, that's just the general solution to the homogeneous equation. Then we'll find a particular solution, which we call y sub p. That's a particular solution to the original problem, the inhomogeneous problem. And then we'll find the general solution by just taking the sum of y sub c plus y sub p. All right, so let's get started. So our first step of our plan is to find y sub c, the complementary function. So we write down the associated homogeneous problem. That just means we write down the same left-hand side of our ODE. And instead of a right-hand side like 15e to the 4x, we just write down 0. And we solve this problem first. So in operator notation, if we use capital D to represent derivatives, this is equal to d squared minus 3d minus 4 applied to y equals 0. So that tells us that our auxiliary polynomial, p of r, is r squared minus 3r minus 4. We can factor this polynomial to get r minus 4 times r plus 1. And we want to find the roots of this polynomial, so I'm going to go ahead and set that equal to 0. So this tells me that my roots are -1 and 4. It's the two roots of this polynomial. So my complementary function, y sub c of x, this is c1 e to the negative x, that's coming from that root -1 there, plus c2 e to the 4x. That 4 is coming from the other root we have, which is 4. Okay, so we're just going to kind of put this on the back burner, just keep that in mind that we have this y sub c already, and now we're going to focus on step 2 of our plan, which is finding a particular solution y sub p. Okay, so to do this, we start by looking at the right-hand side of our ODE. So look at the right-hand side. I'll call it capital F of x, and that's 15e to the 4x. So we're going to look at this, this function, and we want to determine an annihilator for this function. Determine an annihilator, which I'm going to call capital A of d. This is an operator, and we're going to apply that to the both sides of the ODE. So apply to the ODE. The way we find the annihilator is by looking at the exponent of our right-hand side, if it happens to be an exponential. We look at the exponent, and we notice that if we had gotten this right-hand side, or a right-hand side of this form with an e to the 4x, we would have had a root for our auxiliary polynomial, or a root of that polynomial would have been 4. So that tells us that our annihilator, a of d, is equal to d minus 4, because this operator is associated with the polynomial r minus 4, and that has the root 4, so it would have given us this right-hand side, e to the 4x. It would have given us that as a solution. All right, we've got our annihilator. We go ahead and apply that to both sides of the original ODE. And we chose the annihilator specifically so that when we apply it to both sides of the ODE, the right-hand side in particular becomes 0. Because if I apply the operator d minus 4, or a first derivative minus 4 times the original function, this function is going to become 0 if I apply that. So we apply that to both sides, d minus 4. And I'm going to write our original operator slightly differently. So if we go back to the operator we have up here for our homogeneous problem, we can factor that. So notice that it's actually d minus 4 times d plus 1. So that's the way I'm going to write it down here. So just a note that we can factor that. So d minus 4 d plus 1. We're applying that to y. And when we apply that operator to the right-hand side, it is an annihilator of our right-hand side, so it actually gives us 0. And just to reiterate, this part here is just the operator from our original ODE. I just factored it. Okay, so this gives us, we have two copies of d minus 4 here, so I can write this as d minus 4 squared times d plus 1, or I guess applied to d plus 1, it's not really multiplication, applied to y equals 0. Okay, so now I have this new homogeneous ODE. It's not quite the one that I started with, but it's related. So I want to write down the general solution to this problem, and that's going to tell me what the form of my particular solution for my original problem would look like. So let's go ahead and write down the general solution for this one. To do that, we would need our a polynomial. So the associated auxiliary polynomial for this new ODE is r minus 4 squared times r plus 1. So I just used this operator here, replace the capital D's with r's, and that's my auxiliary polynomial. Now the roots of this polynomial are, we still have a root of -1, we have a root of 4, but the root for 4 is actually a repeated root. So 4 is a root twice. When we have a repeated root, we still need to have two linearly independent solutions associated with that root. But we can't just write down e to the 4x twice. We need to do something a little bit more. So the general solution for this ODE would be c1 e to the -x, coming from that root of -1, plus c2 e to the 4x. But now we've got this repeated root, so I need to add an additional thing here. I need to multiply by x, e to the 4x. That gives me another linearly independent solution. Okay, so we're almost there. We want to take a look at this general solution to this new problem. Notice that the first two terms here, c1 e to the -x plus c2 e to the 4x, are the same, have the same form as the solution to the homogeneous problem. So they appear in the complementary function. So we don't want to take those as part of our trial solution. So I'm going to cross these out. Those are not going to be part of our trial solution. Whatever is left over, the terms that don't show up in the complementary function, this term does not show up in that function, so that's going to be our trial solution. So this is our trial solution. That means we're going to plug this function into original ODE and figure out our particular solution. So I'm going to go ahead and write it over here. This was all to say that our particular solution will have the form of a constant. I'll just call it A. I know here I called it C3. You could call it C3 again if you want, but I'm just going to call it capital A so I don't have to deal with subscripts. And then it's x e to the 4x. So this is our trial solution. Our next step is going to be to substitute this trial solution into the original ODE and figure out what this constant A needs to be in order for us to satisfy the ODE. Okay. So I'm going to go ahead and scroll down for that. Okay. There we go. Okay. So very briefly, just have some notes here to remind us what we've done so far. We have our original ODE, we've got our complementary function, and we have our trial solution, which we just found earlier. We're going to substitute the trial solution into the ODE and figure out what this constant A needs to be. All right, so to do that, we're going to need a first derivative and a second derivative. So let's remind ourselves. So y sub p has the form ax e to the 4x. And let's go ahead and take some derivatives. So the first derivative of this function, we have to do a product rule, remember, because we've got two functions here that are multiplied. They both depend on x. So we do a product rule, we get a e to the 4x plus 4a x e to the 4x. And we're going to need a second derivative. So I will take the derivative of this expression. And you'll have to do a chain rule here and then a product rule and a chain rule here. If you do all of that, you'll end up with 16ax e to the 4x plus 8a e to the 4x. So there's a little bit of algebra happening there that I didn't write down, but it's just coming from taking the derivative of this again and then kind of simplifying. All right, so we're going to go ahead and plug these expressions into our original ODE. So we've got y double prime is 16a x e to the 4x plus 8a e to the 4x minus 3 times y prime is a e to the 4x plus 4a x e to the 4x minus 4 times y sub p, so that's just a x e to the 4x. And when that's equal to, we set that equal to our right-hand side, 15 e to the 4x. Now, just as a reminder, let me get a new color here. So this expression is y double prime, this expression is minus 3y prime, and this expression is minus 4y. So you can see that's the left-hand side of our original ODE. Okay, and we combine like terms. So if you combine like terms here, so I'll just combine things that have x and e to the 4x. So that would be a 16a x e to the 4x and this 4a e to the 4x. And we also have, it's going to be a negative 12 a e to x e to the 4x. And then I combine things that don't have an x next to them. Okay, so that's going to give me 16a minus 12a minus 4a. Those are the coefficients on the terms that have x e to the 4x. Plus, then the coefficients on the terms that just have e to the 4x next to them is 8a minus 3a. And we're setting that equal to 15 e to the 4x. Now here we've got 16 minus 12, which is 4, minus 4. So this actually goes away. This is going to be 0. And we're just left with 5a e to the 4x, that's coming from this term here, equals 15 e to the 4x. I'll write that slightly neater. Okay, now e to the 4x on both sides here, that's never going to equal 0, so we can divide through, cancel those out, and we get 5a equals 15. That tells us that a needs to be 3 in order for this particular solution to satisfy the ODE. So we've got y sub p. Remember, y sub p has the form ax e to the 4x, and I just found out that a is 3. So I'm going to replace a here by 3. So y sub p is 3x e to the 4x. That is my particular solution. All right, we're almost ready. We're almost done. We're ready to write down our general solution. So let me just scroll down to the next page here and remind ourselves what we have. We've got our original ODE. We found the complementary function first. That was the solution to the homogeneous problem. And we just found our particular solution. So in step 3 of our plan, so if you remember our plan from the beginning, step 3 is to write down the general solution. So the general solution to our original ODE, y double prime minus 3y prime minus 4y equals 15 e to the 4x, is given by y of x. It's the sum of the complementary function plus a particular solution. And so we write down the functions we found there, c1 e to the negative x plus c2 e to the 4x plus our particular solution, 3x e to the 4x. So this is our general solution to our inhomogeneous ODE.